Hi, in this chapter we're going to discuss about optical sources for the application in optical fiber technology. In this chapter we're going to have a short review on semiconductor physics, and then later on we will going to discuss further about the light emitting diode and later on laser diode. For the application in optical fiber technology, there are some considerations that we need to take into account. First of all, the size or physical dimension must be suitable with our fiber, as you know that the size of the fiber is very small. In that sense, it is smaller even than the thickness of our hair, which is around less than 100 micron. And then in order to couple into the fiber, right, the light source need to couple into the fiber, we need a narrow radiation pattern, or we can see in terms of beam width, it must be smaller as well, so that it is easier for us to couple into the fiber. Other related factor is in terms of linearity. It must be proportional, right? The power output must be proportional to the driving current, so that it must be easier to control the signal. And then with that is related to the ability to directly modulate it by varying driving current. This is related to the modulation process. And when we're talking about optical fiber communication technology, it is about a very fast response, very fast process. So we need a fast response time as well, and has to be a wide band application, and the power must be enough that we can provide into the fiber. Other consideration, the spectral width must be very narrow, right? It must be stable and efficient at the same time, and we need to take into account the driving circuit issues, and other is regarding the reliability and cost that is involved. In terms of review on semiconductor light sources, we're going to need to visit a PN junction, the basic PN function, that consists of direct band gap semiconductor material, and it will act as the active region, or also called recombination region. When we have two different type of semiconductor, we have p-type and n-type. When we combine them together, we're going to have a PN junction, and we can either do a forward bias, means that we put the positive on the p-type and negative on n-type. Then we have it in the forward bias form, and we will have the motion, or the electron, the carriers, the motion, the movement of carriers, which is electron and holes. They will recombine, and it could be either radiatively, or means that it emits the photons, or it could be non-radiative, means that it doesn't emit photon, but instead we have heat involved. And this is basically a simple LED operation. That is for LED. For a laser, the photon, instead of just a spontaneous recombination, we have the photon keep on bouncing in the cavity, and then later on we're going to have a coherent highly directional optical beam with narrow line width, and this type of emission is referred to as stimulated. And that is part of the acronym of laser came from. And if we compare the output of LED versus laser, we can see that for this is referred to LED spectrum, which is about 30 to 50 nanometer wide. And for normal laser, we have much smaller spectral width, which is about 1 to 3 nanometers. And for a single frequency laser, we have much smaller spectral width, which is less than 0.04 nanometer. Right. As you can compare as well the intensity, right? This and this much higher compared to LED intensity here. Alright, for semiconductor physics, the simple semiconductor physics, as we can see, any semiconductor consists of this type of diagram. We can simplify them into this type of diagram, where we have the bottom is valence band and the top is conduction band. Right, when the electron is excited, right, it will move to from valence bands to conduction bands, and when it moved, it left empty spaces here, and these empty spaces is referred to as hole. And with the presence of electric field, it will drift accordingly to this side, while hole will drift to this side. And the spaces or the gap between the conduction band and valence band is what we know as energy gap, and it's depend on material, on the specific material. For example, silicon has energy gap of 1.1 electron volt, and so on and so forth. In terms of concentration, for intrinsic semiconductor, we have about the same number or same concentration of electron and hole at the conduction band and valence band respectively. For n-type semiconductor physics, we can achieve n-type by doping. Alright, and for example, we can dope silicon with phosphorus, arsenic, and so on and so forth. When we add the extra atom or impurity, we provide extra electron, and this we call as donor atom. In this type of semiconductor, n-type semiconductor, we have electron become the majority because we add more donor, and donor carries more electron, and electron become the majority charge carriers, and oppositely, holes become minority carriers. As we can see here in the diagram, we have donor atom here, and it carries as well the extra electron or free electron, and this free electron is free to move, and if we have a lot of them, then we have higher concentration of this free electron. For p-type semiconductor, it is the opposite. We dope the atom, the semiconductor, with boron, right, or other material as well that has less electron. And the atom that we add is called acceptor atom, right? Because they will accept the missing, the electron is missing, and it made them have a empty empty spaces there, what we call as holes. And if you have a lot of them, then we have the majority of charge exists in this material is holes, right? And oppositely, electron become minority carriers. For intrinsic material, it is considered as a perfect material with no impurities, right? We don't add any other material inside the semiconductor itself, right? However, for extrinsic material, as we saw earlier, we add donor or acceptor, and then it will become n-type or p-type semiconductor. Right? Majority carriers in n-type semiconductor is electron, right? For minority carriers in n-type electron, it will be hole, and in opposite, hole will become majority carriers in p-type, and it will become minority in n-type semiconductor. The operation of semiconductor device is basically based on the process of injection and extraction of minority carriers. Alright, when we have two different semiconductor material, p-type and n-type, as we can see here, when we combine them together, as we can see here, right? What happened in this case, we have the minority carriers in p-type, right, will approach the interface, right? And the same case happened for the n-type material. The minority carriers will approach this side, the interface, right? And they will form so-called depletion layer or depletion region, right? This is the case where we don't provide any bias, or we don't provide any electrical field. Right, what happened when we bias the PN junction? Let's see what if we do the reverse bias. Right, means that in reverse bias condition, we put negative to the we put negative to the p-type semiconductor, and we put positive terminal to the n-type semiconductor. And when we do like this, the majority carriers will be attracted to the negative terminal, right? And at the n-type, right, the majority carriers will be attracted to the contact, right, to the electrode. And with this kind of configuration, we only have minority carrier that is flow inside the junction, right? And when minority carrier flow, we have the increase of the depletion region, or what we call as the depletion region is widened. And if we do the forward bias, right? When we do forward bias, we have the minority carriers start to approach the other side, right? And when that happens, we have a small layer of depletion region, right? And with this small layer, we can have the majority carriers, right, can flow across the junction. Right, that happens when we do a forward bias, means that negative will attach to the n-type and positive will attach to the p-type. Alright, and this is basically a simple diode operation. Other information is about the type of semiconductor. We have direct and indirect bandgap semiconductor. For direct bandgap semiconductor, it refers to the position in K vector, the maximum of valence band and minimum of the conduction bands is coincide at this particular point. And when the electron make the transition, it is a direct transition. And this type of transition for this semiconductor is called direct bandgap semiconductor. For example, direct bandgap semiconductor given by gallium arsenide. However, for indirect bandgap semiconductor, we have the minimum of the conduction band. It is not coincide with the maximum of the valence band, and therefore we don't have a direct transition for this case. Right? And the simple example for indirect bandgap semiconductor is given by silicon.